Hello, this is John Adgate. This is a three-part lecture on physical hazards, exposure, and health effects. Now, the learning objectives of the three-part lecture are to be able to describe and understand the potential environmental and occupational health impacts of these four kinds of physical hazards. In this lecture, I'm going to talk about ionizing radiation. This is also the longest of the three parts. In the other two parts, I'm going to talk about noise and lasers and thermal stress. So basically, what I want you to be able to understand is how exposure is measured and what sort of health effects are associated with each one of these physical hazards. Now, this is a reminder to you of something you saw probably in high school science, high school physics. This is the electromagnetic spectrum, and a lot of things we're going to talk about are on this spectrum. So what you see here is what's called long waves to all the way up to gamma rays. And on the left scale, you've got frequency in hertz. And then on the right scale, it's wavelength. And these two things are related, obviously. The higher the frequency, the shorter the wavelength. And these things are also related to different kinds of electromagnetic radiation. For example, what we're used to is visible light, which is the color scale here that runs between 700 nanometers to 400 nanometers on the right is where visible light is. So it's striking that how small this particular range of visible light is within the larger electromagnetic spectrum. Now, if you look, for example, the example on the left is where radio and TV waves are. So those are considerably longer, and they get used to produce what used to be an important distinction, UHF versus VHF, which is really not one of much importance anymore unless you're watching, because so few Americans watch TV over the airwaves. But just keep this in mind, and if it's hard to remember this, perhaps you could remember this next slide, which is a comic of the electromagnetic spectrum by the great comic XKCD. Now, a lot of this is jocular, but again, this shows you where visible light is, and a lot of this is actually based on science. It shows you some units at the bottom, but then there's some interesting things like blog rays, gravity, Superman's heat vision, so on and so forth. But if any of this helps you sort of understand the phenomena here, the part of power and telephone up to cosmic and gamma rays, and the gray boxes at the bottom are actually mostly correct, except for the part about censored under the Patriot Act. But you get the idea here, and I think this is sort of a creative way to look at it. All right, so in this lecture, we're going to talk about ionizing radiation. Now, if you go back to the lecture on war and environment, we talked about the health effects associated with that, but now I want to talk just a little bit about what that actually is. So there's a lot of different forms of radiation and radioactive materials that are a part of our life because they're a natural phenomenon. So we're constantly exposed to low levels of radiation from outer space, the Earth, and believe it or not, via medicine. And low levels naturally occur in radioactive materials in our environment, in the food we eat, and many consumer products. And some consumer products also contain small amounts of man-made radioactive materials. Now, what you see at the top here is the aurora borealis, which is related to radiation and is a natural activity. If you look down below that, there's two items that you may or may not have in your house. On the left is what's a Fiesta-ware plate, and believe it or not, when these are produced, they put just a little bit of uranium in the orange plates, at least the original ones for the 1950s. And if you can get them from a collector, you can put them next to a Geiger counter, and it'll actually the number of counts will go up. Now, things that you may have in your house that you're a little more familiar with is, believe it or not, there's a little bit of radiation in smoke detectors because they use ionization to detect smoke. So radiation has a lot of beneficial uses, but probably the most common one that you're aware of is the smoke detector in your house. So a little bit of background, because we're going to talk about ionizing radiation. Here's the basics for those of you who might have forgotten Chemistry 101. Atoms are made of two basic parts. There's the nucleus, which has the protons and neutrons, and the electrons orbit the nucleus. Now, the nucleus is typically positively charged. Protons have a positive charge. Neutrons have no charge, but the combination of those two give you the atomic the atomic weight. Atomic number is the number of protons. Mass number is protons plus neutrons. Now, elements are in their native state neutral, so there's an equal number of protons and electrons, and they vary some in their weight because you may have an unusual number of neutrons, i.e. more than the number of protons. Now, unstable isotopes exist because they've got, for example, one proton and two neutrons, what's known as tritium, which is one of the three isotopes of hydrogen. The other two are deuterium and proterium. Now, proterium, hydrogen is the simplest atom. It's just one proton and one electron. But these, when you've got either too few neutrons or too many, it makes the nucleus less stable, and as a consequence, you get what's called a radioisotope. And the unstable atom will become stable by giving off excess energy. The energy is in the form of particles or rays, which is essentially what radiation is. Now, these unstable atoms are known as radioactive atoms or radioactive isotopes, and they have a lot of beneficial uses. Now, one of the key concepts with radiation is what's called both decay and half-lives. So these unstable atoms transform themselves over time, and it transforms from the unstable states to stable states, and in the process will release energy or radiation. So the number of decays per unit time is a measure of radioactivity or relative radioactivity. It's commonly called Curies after Madame Curie, i.e. decays per minute, or becquerels, or BQ, which is decays per second. Now, half-life is the amount of time it takes for a substance to decrease by half. So you go from the isotope that is unstable. If half of them decay, that's the half-life. If the new isotope is also unstable, that creates what's known as decay chain. And what's on the left here is the decay chain for uranium, which goes from uranium to thorium to all these other, and notice that it goes back to uranium-234, but all these other elements over time. We'll talk about radon and some of the others later on, but ultimately when uranium breaks down over time, uranium-238 eventually becomes finally a stable isotope of lead-206. But that's over many millions of years. Now, the other way to sort of visually see this is the example at the bottom, which shows sort of decay rate over time and the number of half-lives. If something is almost entirely filled up with particles that are going to, or atoms that are going to decay on the left, you can see how each one of these, from moving from left to right, one of those boxes, about half of the dots turn from black to yellow. And in the end, you can see from the beginning, the block is almost completely black from the particles, the black dots. But even after 9 half-lives, there's still a few left because it's a stochastic process. So after 10 half-lives, the level of radiation is reduced to 1/1000th is the rule of thumb. All right, so some important isotopes that we're usually familiar with and or you've likely heard about, and then their half-lives. For example, uranium, the half-life is actually billions of years. and largely because your natural uranium is composed of several different isotopes. Typically, what we use in nuclear reactors is uranium-235. Also happens to be in nuclear weapons. Now, other things get used for other purposes. For example, carbon-14 gets used for dating, but it also gets used to radiolabel tumors with some drugs. And some things get used in the laboratory. For example, tritium, hydrogen-3 with a half-life of 12.3 years gets incorporated into proteins or other compounds, and to see how they react physiologically or get used in physiological processes. Now you can see others. Sort of iridium is used for treatment of cancer, and there are a bunch of others that get used for therapeutic or diagnostic reasons. So one of the takeaways from this slide is it's by no means exhaustive, but there's a lot of different useful a lot of different useful isotopes, I should say. So the reason to tell you about the background chemistry, just as a reminder, is what we're really interested in with radiation is ionizing radiation, and there's various types, as you can see in this slide. So there's what's known as particulate and photon or electromagnetic radiations. Now, the particles are either alpha, beta, or neutron, and you can see them here. They're depicted. Whereas the electromagnetic photon radiations have no mass and no charge, but they have a wavelength and a frequency, and those are X-rays and gamma rays. So an alpha particle is 2 protons and 2 neutrons. It's essentially the same thing as a helium nucleus. A beta particle is essentially just an electron that escapes, and a neutron is a neutron. So electromagnetic or particle radiation can cause biological damage, and the factors that affect that are the two that are outlined here. One is just the amount of energy, which is typically measured in kilo electron volts or mega electron volts, and it's how much of the energy gets absorbed by a tissue. So higher energy radiation of the same type will penetrate further than a particle with lesser energy, or a ray with lesser energy. Now, the other part of that affects biological damage is what's called linear energy transfer, which is essentially measured by the ionization density, the number of ion pairs per centimeter of tissue along the path of the radiation. Now, these things tend to travel in straight lines until they hit something. So LET, the linear energy transfer, is affected by mass of the particle and energy, and higher LET causes greater biological impact and is assigned a higher what's called quality factor, or a radiation weighting factor. So these are the key points of radiation dosimetry: is how much energy and how much energy gets transferred over the path. So I'm going to walk you through the basic particles and other types of radiation and talk about what sort of damage they cause. So an alpha particle is positively charged. It's a high energy uranium nucleus that has been expelled from an atom. It has a pretty large mass and a lot of energy, and therefore a high LET. Now, the flip side of that is they don't travel very far. They only travel about 10 centimeters in air on average, or 60 microns in tissue, because they'll hit something and stop. So as a consequence, these sort of particles are easily shielded. A piece of paper or dead layer skin will protect you from an alpha particle if it hits your skin, which is, remember, our skin is all just dead cells. Alpha particles are a bigger issue when they're emitted in, for example, your lungs, but we'll get into that when we talk about radon a little bit. So as an internal hazard, it deposits large amounts of energy in a small amount of body tissue, which is why alpha particles and radon is such a hazard. Now, beta particles are just an electron being emitted from the nucleus. So they're high speed, They have a negative charge, but they have very low mass, even though they have very high energy. As a consequence, they can go about 12 feet in air and a few millimeters in tissue. But they have very low LET. They're not going to go very far, so relatively low quality factor. You can shield beta particles with something like plastic. They can be an internal hazard, but high concentration of beta particles can be a hazard to eyes and skin. So the last kind of particle radiation is neutrons when they're ejected from a nucleus. Now they have the same atomic mass as a proton, but no charge. But once they're out of the nucleus, they are unstable and decay by beta emission. So what they do is they become positive, they become a proton because they eject an electron. Now this happens pretty quickly. You can see the half-life is 13 minutes. Now the range of these things is several hundred feet in the air, and they have very high penetrating power due to the lack of charge, and as a consequence they're difficult to stop. These are very small particles, traveling. So the range and the LET are dependent on the speed of the neutron, which is depends on how much energy it has. So there's either slow thermal or slow or fast, I should say. Slow are referred to as thermal neutrons. You can see here that the quality factor goes from 3 to 10 as the energy level goes up. Now these can be shielded in stages. Sort of high-speed neutrons are thermalized by elastic collisions with hydrogenous materials like water or paraffin or concrete. But slow ones are captured by secondary shielding materials like boron or cadmium typically. Now, their main hazard is external whole body exposure as opposed to internal exposure. So that's the main problem and sorts of health effects associated with whole body exposure. So we talked about alpha, beta particles, and neutrons, and now we're going to shift to gamma radiation and X-rays, which are sort of two photon-based forms. So gamma radiation is electromagnetic radiation or photons emitted from the nucleus. So they don't have any mass or charge, and they move at the speed of light. Very high energy, and they go for a long ways. They can go for kilometers in the air, but they have relatively low LET and can be shielded with concrete, water, or lead. Now their biological hazard is sort of whole body exposure. If you get particles or gamma radiation with greater than 70 keV energy levels, it can penetrate tissue. So we're most familiar with X-rays, which are electromagnetic radiation or photons produced from orbiting free electrons. Now these can be artificially created when electrons strike a targeted material inside an X-ray tube and are emitted with various energies and wavelengths. Typically these are lower energy than gamma rays, so it's keV rather than MeV. But they have similar levels of penetration and shielding and biological effects to gamma rays. Now, if you go to the dentist's office, for example, you're probably familiar with having your X-rays taken, and they'll put some shielding on you, usually a heavyweight sort of cloth item that's got some metals in it, like lead, to help protect you, because you don't need a very thick layer, but you do need it to shield you from the effects of these, unless you're, of course, Homer Simpson. So we've talked about 5 kinds of radiation, either the 3 particles, alpha, beta, or neutrons, and the 2 rays, gamma or X-ray. Now these can either cause, as I mentioned, direct tissue damage when they hit an organ like your skin, or they can cause cellular damage by producing free radicals or damaging DNA. And typically when cells are damaged, this activates the cellular repair process. Now, as we're exposed all the time to particularly X-rays and gamma rays from the atmosphere. In fact, if you fly in a plane, you get a bigger dose than you do at the ground, uh, because you're closer to the source. Similarly, living in Denver, for example, you get a bigger dose of radiation than you do living at sea level, because there's more atmosphere between you and the source that provides some shielding. Regardless of this, it's the repair process that gets activated, and which is important because all of us receive some radiation exposure and a little bit of background damage that is repaired continuously over time. So the good news about all this is our bodies are resilient. We have pretty highly efficient DNA repair mechanisms, and this is needed because DNA damage, for example, is really important and can lead to cell malfunction, i.e. cancer, or cell death. We have about 60 trillion cells, and each cell takes a hit from radiation and or internal chemical stressors about every 10 seconds, resulting in tens of millions of DNA breaks in each cell per year. So that repair process is important. Now, if you think about this, the sort of chemical hits from either external toxicants or things created in the cell are much more frequent than those caused by background radiation. Background radiation or exposure above background can have bigger effects, but the point of this is background radiation only causes a very small fraction of these sort of breaks or hits, approximately 5 DNA breaks per cell each year. Is from background, which is again, it's good we have efficient repair. So cells that are rapidly dividing are the most radiosensitive, and that sort of makes intuitive sense because essentially because there's less time to do repair. Examples of these sort of rapidly dividing cells are things like blood-forming cells, your bone marrow, your intestinal lining, which you shed every couple of days, so there's a lot of cell division going on there. Things like hair follicles, and rapidly growing bodies such as a fetus in the womb. Now, as a consequence of this, we have very different health-based standards for pregnant women and the child they're carrying. You can see that it's 1/10 of the annual adult exposure limit for those who are occupationally exposed. So here's a table just showing you from very high to low various tissues in terms of their relative sensitivity. So as I mentioned, rapidly dividing things like white blood cells, the intestinal epithelium, and reproductive cells are relatively sensitive to the effects of radiation, whereas things like mature red blood cells, muscle cells, and mature bone and cartilage are not. And then you can see some things that are in between. Things that are high, that are highlighted here, are things like your eyes, the optic lens epithelium, and mucous membranes in your respiratory and intestinal tract tend to be pretty sensitive as well. So a little contrast to the chemical exposure assessment, which was, remember, a dose, as defined in the exposure assessment lecture, was a mass of some toxicant, typically expressed in units like micrograms or milligrams, and usually normalized to body weight. With a dose of radiation, it's the amount of energy as opposed to the mass that's deposited in body's tissues. That's a dose of radiation. And the more the energy is deposited into the body, the higher the dose. Now, so this is related to both the energy and the quality factor. So there's a couple different ways to sort of express this. One is called a REM, which is a unit of radiation dose. The international unit, or the sign, is called a sievert, which is equal to 100 rem. And then smaller doses get expressed in millirems. Now, there's other units that you'll hear about that are a little older. They're not the SI units, the RAD or R for Roentgen, but they can be converted to REM, and I think REM is the most useful one to think about. Well, There are both exposures and health effects associated with all radiation, and similar to what we discussed in the tox lecture, we have both acute and chronic doses. So large doses or acute doses of radiation over a short period of time may result in observable health effects like nausea and vomiting usually are one of the first things you see, but then eventually things like hair loss, fatigue, and medical complications. The burns caused by radiation and wounds tend to heal pretty slowly, and some of these are sort of intentional in the sense of medical exposures, like radiation to kill tumors, but there's also accidental exposures that you sometimes get in the workplace that are acute in nature. The more chronic dose is obviously what's received over a longer period of time, and the body typically more easily repairs damage from chronic doses, and may not result in observable effects such as background radiation or internal deposition. Although it may not be observable, but there may be long-term health effects. So let me show you sort of the typical doses that people receive in a year. You can see here in this table, the average dose of the U.S. public from all sources is about 360 millirem a year. And approximately a little less than 60 of that is due to medical uses. And you can see some of these other sources from weapons fallout, coal burning, nuclear power, and then you can see some of the other things that are relatively common. Now, a coast-to-coast airplane plane trip is not much less than a chest x-ray or a dental x-ray, which is a little bit more. But you can see some other things. I'll show you an example of a fluoroscope in a minute, but these are things that were used at one point. But note the occupational dose limit in yellow here for radiation works is typically 5,000 millirem per year. So you can see that most typical exposures are a whole lot less than the occupational exposure limit. Now, at high doses, we do know that radiation causes harm. Now, I mentioned in the last slide the fluoroscope, and that's what this woman is doing here. She's got a fluoroscope, and these were used, believe it or not, around the United States early on for a number of years. There's a museum of quackery that used to be open in Minneapolis that had a bunch of these. You could literally go in, and they were, believe it or not, used in shoe stores as ways so people could see the bones in their feet, and ostensibly to measure their foot size. But you have seen a number of different high-dose cohorts that have been developed over time as people who were radium dial painters. They were mostly women who were literally painting watch faces using these glowing paints that were used on watch hands, but people who were radiologists before radiation control got to be a lot better, people who survived the atomic bombs in Hiroshima and Nagasaki, the populations near Chernobyl and Fukushima, and other intentional high doses might be medical treatments, but also accidents around criticality at nuclear reactors. So in addition to radiation sickness that people got in all these cases, increased cancer rates have been evident from high-level exposures for a long time. So the long-term effects of radiation are in contrast to the acute ones. Radiation does, in the chronic sense, increase one's risk of cancer. Now, your normal chance, quote unquote, of cancer is about 23%, or 1 in 4 over your lifetime. Or in this case, it says it's a little more precise, 460 out of 2,000. So each rem of exposure is assumed to increase risk by about 0.05%, or about 1 chance in 2,000. Now, look at this in contrast to the occupational radiation dose limit for the whole body is 5 rem, or 5,000 millirem from a couple slides back. So note that the odds are relatively small, but they're not zero. So as a consequence, what what we ought to focus on from a public health perspective is reducing radiation exposure. So you want to minimize the time one is exposed. You want to be further away. Doubling the distance from a source typically decreases your exposure by about 4-fold, and having some sort of shielding tends to help. Lead-coated walls and personal protective equipment are two of the most common ones, and you'll get some sort of coating on walls, for example, in a dentist's office, and here's somebody wearing one of the typical shielding smocks that you get asked to wear when you get your x-rays done. So radon, you've probably all heard about radon if you've lived in Colorado for a while, because we're a high radon state. Radon is a gaseous decay product of U-238 decay series, which you can see here. Everything else in this decay series is a solid, but as a consequence, it's an important environmental health issue. Now, radon is often present in areas with high granite or shale soils, and it enters homes through cracks in the basement, and can also enter through well water in a lot of cases, although the cracks in the basement is the principal way one gets exposed most typically, and it's also why the levels in houses are typically highest in the basement. So here's a map of sort of high versus low radon levels. The zone 3 are the yellow here are the lowest, 2 the orange is medium, and 1 is red is the highest, and these are the places with more granite soils, and typically homes have higher radon levels in these states and regions. And you can see that's principally around the Appalachians, and in shale and granite substrata in the Midwest, all the way out to the west. Now you can see other places, other parts of the country where levels are a lot lower. So radon is important because it's a leading cause of cancer amongst non-smokers. It's estimated that it's somewhere between 15,000 and 20,000 deaths are caused by radon-induced lung cancer in the United States every year. So you can see that's a non-trivial number. Now, as a consequence, EPA has created this health-based guidance. It's not actually an enforceable standard, but it recommends that you keep radon levels below 4 picocuries per liter of air in your homes. Well, the good news is that residential radon mitigation is relatively easy and relatively inexpensive to do. Colorado is a high radon state, as I mentioned, but these sub-slab depressurization systems are really effective and affordable. I have one on my own house that was installed when I bought it. What it is essentially is a pipe that goes underneath the slab in your basement, and it pulls the radon out. Radon tends to, the gas tends to accumulate under slabs because that's sort of a low pressure zone. If you think about your house being a straw stuck in the soil, it has some capillary action, and that for homes without these mitigation systems, the basements are the place where radon levels are the highest. So what you do is you pull the radon and other air out from underneath the slab and emit it outdoors, where it quickly reaches the point of background concentration. And by doing that, you have mitigated the radon issue in your home, or at least you've reduced it to a level that's below the level of concern that EPA has developed. So this ends part 1 of this physical hazards lecture.